Close your eyes and take a deep, calming breath. Let your body sink into complete relaxation. Tonight, we're going on the most peaceful journey imaginable. Traveling through the infinite cosmos, discovering the gentle truths about the universe that surrounds us. Let these soothing facts about space, stars, and the vast beauty of existence carry you into the deepest, most restful sleep. Imagine yourself floating in the softest darkness, weightless and perfectly comfortable. Above you, below you, all around you, stars shine with patient light. You're safe. You're calm. You're about to discover that the universe, despite its incredible size, is a place of profound peace and timeless beauty. The universe is ancient beyond comprehension. It began approximately 13.8 billion years ago in an event we call the Big Bang. Everything that exists, all matter, all energy, all of space itself, emerged from that single moment. Every atom in your body was forged in that ancient beginning, or in the hearts of stars that lived and died billions of years ago. You are literally made of stardust. You are the universe experiencing itself. Space is mostly empty. The distances between objects are so vast that if you could travel at the speed of light, it would still take years to reach even the nearest stars. This emptiness isn't lonely or cold in a sad way. It's peaceful. It's quiet. It's the ultimate silence, undisturbed by sound, because there's no air to carry vibrations. In space, there is only light and darkness, matter and void, moving in elegant patterns that have existed for billions of years. The speed of light is the ultimate speed limit in the universe. Nothing can travel faster. Light moves at 186,000 miles per second. At that speed, you could circle the Earth 7.5 times in just 1 second. Yet, the universe is so large that light from distant galaxies takes billions of years to reach us. When you look at a star, you're seeing it as it was years ago. You're literally looking back in time. The night sky is a window into the past. Our sun is just one star among hundreds of billions in our galaxy. And our galaxy, the Milky Way, is just one galaxy among hundreds of billions in the observable universe. The numbers are so large, they lose meaning. But here's what matters. Despite this vastness, despite being such a tiny part of something incomprehensibly large, you exist. You matter. You're here, conscious, able to contemplate these mysteries. That alone is miraculous. The Milky Way galaxy is a spiral, like a cosmic whirlpool of stars. If you could see it from outside, you'd see elegant arms of stars spiraling out from a bright central bulge. Our solar system sits about halfway out on one of these spiral arms. We're rotating around the galactic center, completing one orbit every 230 million years. The last time Earth was in this position, dinosaurs were just beginning to evolve. The galaxy moves slowly, patiently, in rhythms that span geological ages. There are more stars in the universe than grains of sand on all the beaches on Earth. Think about that for a moment. Every tiny grain of sand multiplied across every beach, every desert. The stars outnumber them. Each of those stars is a sun, many with their own planets, their own systems. The scale is humbling and somehow comforting. We're part of something so much larger than ourselves. Our daily worries shrink to nothing against this backdrop of cosmic grandeur. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse at the end of their lives. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners sucking up everything nearby. They only affect objects that come very close. From a distance, they're as harmless as any other massive object. They simply sit there, patient, marking places where stars once shined, now transformed into something new and strange. At the center of nearly every large galaxy, including our own, sits a supermassive black hole. These giants contain millions or billions of times the mass of our Sun. The black hole at the center of the Milky Way is relatively quiet, not actively feeding. It simply exists, a dense point around which hundreds of billions of stars orbit. It's been there for most of the galaxy's history, a silent anchor, a gravitational heart around which our cosmic home revolves. Neutron stars are the collapsed cores of massive stars. They're incredibly dense. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. These stars are typically only about 12 miles across, yet they contain more mass than our Sun. Some neutron stars spin rapidly, emitting beams of radiation like cosmic lighthouses. These are called pulsars. They rotate with such precision that they're more accurate than atomic clocks. The universe has its own perfect timekeepers. The universe is expanding. Every galaxy is moving away from every other galaxy. The space between them is stretching, growing. This expansion was discovered in the 1920s and revolutionized our understanding of the cosmos. The universe isn't static. It's dynamic, changing, growing larger with each passing moment. In billions of years, the universe will be much larger than it is now. Galaxies spread farther apart. The spaces between them vaster and darker. Dark matter is one of the great mysteries of the universe. We can't see it directly. It doesn't emit, absorb, or reflect light, but we know it exists because of its gravitational effects on visible matter. Dark matter makes up about 27% of the universe. It's the scaffolding on which galaxies form, the invisible framework that holds the cosmos together. We don't know what it is yet, but we know it's there, silent and pervasive. Shaping everything, dark energy is even more mysterious. It makes up about 68% of the universe. It's the force causing the universe's expansion to accelerate. Galaxies aren't just moving apart. Dark energy is pushing space itself to expand. We don't understand it. We can measure its effects, but not explain its nature. The universe is mostly made of things we don't understand. There's comfort in that. There's still so much to discover, so many mysteries waiting to be solved. Our solar system formed about 4.6 billion years ago from a cloud of gas and dust. Gravity pulled this material together, and at the center, pressure and temperature became high enough for nuclear fusion to begin. Our sun was born. The remaining material formed planets, moons, asteroids, and comets. Everything in our solar system comes from the same cloud, the same material. Earth and you share a common origin. We're all family, born from the same stellar nursery. The sun is a medium-sized star, neither particularly large nor small. It's yellow, stable, and will continue shining for another 5 billion years. Every second, the sun converts about 600 million tons of hydrogen into helium through nuclear fusion. This process releases tremendous energy that travels through space as light and heat. That warmth you feel on a sunny day is energy created in the sun's core, released through nuclear reactions, traveling 93 million miles through space to touch your skin. Planets form from the disk of material orbiting a young star. Rocky planets like Earth form closer to the star, where it's warm enough for rock and metal to remain solid. Gas giants like Jupiter and Saturn form farther out, where it's cold enough for ice and gas to accumulate. This pattern is common in planetary systems across the galaxy. The architecture of our solar system follows universal physical laws. We are different in details, but similar in structure to countless other planetary systems. Orbiting distant stars, Earth is the only place we know of where life exists. This might seem special, and it is, but the universe is so vast, with so many stars and planets, that most scientists believe life must exist elsewhere. We simply haven't found it yet. The universe is young. In cosmic terms, life on Earth appeared relatively quickly after the planet formed. If life can start here, it can probably start elsewhere, too. We might not be alone. The universe might be full of life, waiting to be discovered. Asterisk, the moon, is Earth's companion, orbiting us at an average distance of about 239,000 miles. It formed about 4.5 billion years ago, probably when a Mars-sized object collided with early Earth. The debris from this impact coalesced to form the moon. It's been with us ever since, stabilizing Earth's rotation creating tides, lighting our nights. The moon's presence makes Earth more hospitable to life. We're fortunate to have such a companion. The moon is slowly moving away from Earth at about 1.5 inches per year. Billions of years ago, it was much closer. In the distant future, it will be farther away. But for now, for our lifetimes and thousands of generations to come, the moon will be right where it is, hanging in the night sky, waxing and waning through its phases, a constant presence that has guided travelers and inspired poets since humans first looked up in wonder. Lunar phases occur because we see different amounts of the sun. Illuminated side as the moon orbits Earth. New moon when the far side is lit. Full moon when the near side is lit. The cycle takes about 29.5 days. This lunar cycle has influenced human culture for millennia. Many calendars are based on it. Agricultural practices followed it. Stories and myths revolve around it. The moon's phases are a cosmic clock, marking time in a rhythm older than civilization. Mars is the fourth planet from the sun, a cold desert world with a thin atmosphere. It's reddish because its surface contains iron oxide, essentially rust. Mars once had liquid water on its surface. Rivers flowed there. Lakes existed, perhaps even an ocean. But Mars lost most of its atmosphere billions of years ago, and the water disappeared. Now it's frozen at the poles or underground. Mars is what Earth might have become under different circumstances. It's a reminder that planetary conditions can change, that nothing is forever. Jupiter is the giant of our solar system, containing more mass than all other planets combined. It's a gas giant with no solid surface. If you tried to land on Jupiter, you'd sink through layers of increasingly dense gas until pressure crushed you long before reaching any kind of bottom. Jupiter's most famous feature is the Great Red Spot, a storm larger than Earth that's been raging for at least 300 years. The universe operates on different scales than human experience. Storms that last centuries. Planets that dwarf our world. Saturn is famous for its magnificent rings. These rings are made of billions of chunks of ice and rock, ranging from tiny grains to house-sized boulders. They orbit Saturn in a thin plane, held in place by gravity and the gravitational influence of Saturn's many moons. The rings are beautiful, but they're temporary on cosmic timescales. They might be only a few 100 million years old and might disappear in another few 100 million years. We're fortunate to live in an era when Saturn has rings to see. Let's continue our peaceful journey through the infinite cosmos, discovering more gentle truths about the universe that cradles us all. Uranus rotates on its side, tilted at 98 degrees. This means its poles point where most planets' equators would be. Scientists think a massive collision early in the solar system's history knocked Uranus sideways. Now, it rolls around the sun like a ball, its seasons lasting decades. For 21 years, one pole faces the sun in continuous daylight, while the other experiences continuous night. Then they switch. Uranus shows us that even planets can be different, unique, following their own path through space. Neptune is the farthest planet from the sun, a deep blue world of ice and gas. It's so far away that it takes 165 Earth years to complete one orbit. Winds on Neptune are the fastest in the solar system, reaching over 1,000 miles per hour. Yet despite these violent winds, Neptune appears serene from space, a peaceful blue sphere floating in the darkness. Distance and perspective change everything. What seems turbulent up close appears calm from far away. Beyond Neptune lies the Kuiper Belt, a region of icy bodies left over from the solar system's formation. Pluto resides here, along with thousands of other objects. These frozen worlds orbit in the cold darkness beyond the planets, taking centuries to complete their slow journeys around the sun. Their remnants, fossils from the early solar system, preserved in deep freeze. They remind us that creation leaves traces that beginnings echo through time. Even farther out is the Oort cloud, a vast spherical shell of icy objects surrounding the solar system. It extends almost halfway to the nearest star. Comets come from the Oort cloud. Occasionally, gravitational disturbances nudge one of these icy bodies inward. It falls toward the sun, developing a glowing tail as ice vaporizes in the sun's heat. Comets are visitors from the edge of our solar system, messengers from the darkness, briefly blazing bright before returning to the cold dot. Comets have captured human imagination for millennia. Ancient peoples saw them as omens, signs from gods, or warnings of change. Now we know they're simply chunks of ice and rock. But they're still beautiful. A bright comet with a long tail stretching across the night sky is a magnificent sight. Comets remind us that the solar system is dynamic, that objects move through it in long elliptical orbits, that nothing in space is truly static. Asteroids are rocky bodies that orbit the sun, mostly in the asteroid belt between Mars and Jupiter. They range in size from tiny pebbles to Ceres, which is nearly 600 miles across. Asteroids are leftover building blocks of planets, material that never coalesced into a world. They drift through space, occasionally colliding, breaking into smaller pieces. Most are no threat to Earth. They simply exist, silent and patient, following their orbits as they have for billions of years. Meteoroids are small pieces of rock or metal in space. When a meteoroid enters Earth's atmosphere, friction heats it, creating a bright streak of light called a meteor or shooting star. Most meteoroids are tiny, burning up completely before reaching the ground. On a clear night, away from city light, you can see several meteors per hour. Each streak of light is a tiny piece of space meeting Earth, a moment of connection between our world and the cosmos beyond. Making a wish on a shooting star is a tradition in many cultures. There's something special about seeing a meteor, a brief flash that's gone almost as soon as you notice it. Perhaps we wish on them because they remind us that moments are fleeting, that we should seize opportunities when they appear. Or perhaps we simply like having a reason to look up at the sky and think about our hopes and dreams. Either way, shooting stars connect us to wonder. Meteorites are meteoroids that survive the journey through the atmosphere and land on Earth's surface. They're pieces of space you can hold in your hand. Some meteorites are as old as the solar system itself, 4.6 billion years old. Holding a meteorite is holding a piece of the universe's history, a fragment that has existed since before Earth had oceans, before life began. These ancient travelers bring the cosmos to us. Stars are born in nebulae, vast clouds of gas and dust in space. Gravity slowly pulls material together. As the cloud contracts, it heats up. Eventually, the center becomes hot and dense enough for nuclear fusion to begin. A star ignites. This process takes millions of years. Stars are patient in their birth, slowly gathering themselves from the cosmic mist, preparing for lives that will last billions of years. Creation cannot be rushed. The Eagle Nebula is one of the most famous star-forming regions. It contains the pillars of creation, tall columns of gas and dust where new stars are being born right now. These pillars are light years tall, towering structures that dwarf our entire solar system. Within them, stars are condensing from the nebulous material. In a few million years, these pillars will be gone, dispersed by radiation from the new stars they created. The nebula will look completely different. Change is the only constant, even in space. Stars come in many colors. Blue stars are the hottest and brightest, but burn out quickly, living only millions of years. Red stars are cooler and dimmer, but last trillions of years, far longer than the current age of the universe. Our yellow sun is in between, with a lifetime of about 10 billion years. Star color tells you its temperature and hints at its life story. The night sky is a rainbow of stellar colors if you look carefully. Some stars exist in binary systems, two stars orbiting their common center of mass. They're gravitationally bound. dancing around each other in orbits that can last hours or millennia, depending on their separation. About half of all stars are in binary or multiple star systems. Many worlds orbit to suns, seeing sunrises and sunsets that involve two stars instead of one. The universe loves company. Even stars often have companions. Asterisks, red giants, are stars near the end of their lives. When a star exhausts the hydrogen in its core, it begins fusing helium and heavier elements. This causes the star to expand enormously. Our sun will become a red giant in about 5 billion years, swelling to perhaps engulf Earth's orbit. But this, for now, for millions of generations to come. The sun will shine steadily, warming Earth, supporting life. When very massive stars die, they explode in supernova, some of the most energetic events in the universe. For a few weeks, a single supernova can outshine an entire galaxy. The explosion scatters heavy elements into space, material that will eventually form new stars and planets. Every atom of carbon, nitrogen, oxygen, iron in your body was created in stars and dispersed by supernova. You are made of star stuff, forged in cosmic furnaces and scattered across space before gathering. Again here on Earth, white dwarfs are what medium-sized stars like our sun become after they've exhausted their fuel and shed their outer layers. What remains is a hot, dense core about the size of Earth, but containing roughly the mass of the sun. White dwarfs slowly cool over billions of years, eventually becoming black dwarfs, cold stellar remnants. But the universe isn't old enough yet for any black dwarfs to exist. Even the oldest white dwarfs are still glowing faintly. The universe is young enough that some endings haven't happened yet. Variable stars change in brightness over time. Some pulse regularly, expanding and contracting. Others have companion stars that periodically eclipse them. Cepheid variables pulse with a period related to their absolute brightness, which makes them useful for measuring cosmic distances. By comparing a cepheid's apparent brightness to its absolute brightness, astronomers can calculate how far away it is. These pulsing stars are cosmic mile markers, helping us map the universe. The constellation patterns we see from Earth are mostly illusions of perspective. Stars that appear close together in a constellation are often at vastly different distances from us. They simply happen to lie in the same direction from our viewpoint. If you traveled to another star system, the constellations would look completely different. The patterns we know, the shapes we've named, exist only from Earth's perspective. The universe looks different from every vantage point. Ancient cultures saw different patterns in the stars and created different constellations. The Western constellations come from Greek and Roman traditions, with additions from later European astronomers. Other cultures had their own constellations, their own stories written in the stars. Chinese constellations are different from Western ones. Indigenous Australian cultures have constellations that include dark patches of the Milky Way, not just stars. The night sky is a canvas on which every culture has painted its mythology. The North Star, Polaris, has guided travelers for centuries because it appears nearly stationary as Earth rotates. This happens because Polaris is almost directly above Earth's North Pole, while other stars appear to circle the sky as Earth turns. Polaris remains in place, a faithful beacon. But Earth's axis slowly wobbles over 26,000 years, a motion called precession. Thousands of years ago, different stars served as pole stars. Thousands of years in the future, Polaris will no longer mark north. Even the most constant-seeming things eventually change. Light pollution from cities hides most stars from view for much of humanity. People living in urban areas might see only a few dozen stars on a clear night. But from a truly dark location, far from artificial lights, you can see thousands of stars with the naked eye. The Milky Way becomes visible as a glowing band across the sky. This is the view our ancestors had every clear night, this magnificent display that inspired myths and guided navigation. We've lost this in our lit-up modern world, but it's still there, waiting above the glow of cities. The Milky Way appears as a band because we're inside it, looking through the disk of our galaxy. We see more stars when we look along the galactic plane than when we look above or below it. The center of the Milky Way, in the direction of the constellation Sagittarius, is particularly dense with stars. From a dark location, this region is spectacular, a bright concentration of stars marking the heart of our galaxy. This is the direction of the supermassive black hole around which we orbit. Globular clusters are dense spheres of hundreds of thousands of stars orbiting galaxies. They're ancient, among the oldest objects in the universe, formed shortly after the Big Bang. The stars in globular clusters are packed much closer together than stars in the galactic disk. If Earth orbited a star in a globular cluster, the night sky would be spectacular, filled with bright stars in every direction. But such systems are probably hostile to life. The crowded conditions lead to frequent, close stellar encounters that would disrupt planetary orbits. Nebulae come in many types. Emission nebulae glow because their gas is energized by nearby hot stars. Reflection nebulae don't produce their own light, but reflect light from nearby stars. Dark nebulae are dense clouds that block light from objects behind them. Planetary nebulae are shells of gas expelled by dying stars. Supernova remnants are expanding shells of material from exploded stars. Each type of nebula tells a story of stellar birth, life, or death. The Crab Nebula is the expanding remnant of a supernova that was observed on Earth in the year 1054. Chinese and Arab astronomers recorded seeing a new star that was visible in daylight for weeks. That star was a supernova, a massive star destroying itself. Now, 1,000 years later, we see the expanding debris cloud still rushing outward at millions of miles per hour. At the center is a pulsar, the crushed core of the original star, spinning 30 times per second. The Crab Nebula reminds us that even catastrophic endings create beauty. Let's drift even deeper into the peaceful cosmos, discovering more gentle truths about the infinite universe that holds us all. Galaxies come in different shapes. Spiral galaxies, like the Milky Way, have elegant arms winding out from a central bulge. Elliptical galaxies are smooth, football-shaped collections of stars without distinct structure. Irregular galaxies have no particular shape, often because they've been disturbed by gravitational interactions with other galaxies. Each shape tells a story about the galaxy's history, about the forces that shaped it over billions of years. The universe is an artist, creating forms in endless variety. The Andromeda Galaxy is the nearest large galaxy to the Milky Way, about 2.5 million light-years away. It's approaching us at about 70 miles per second. In about 4 billion years, Andromeda and the Milky Way will collide. This sounds violent, but galaxy collisions are gentle affairs. Stars are so far apart that individual stars rarely collide. The galaxies will pass through each other, their shapes distorted by gravity, eventually merging into a single large elliptical galaxy. This merger is the distant future. For now, Andromeda is simply a beautiful spiral visible from Earth on dark nights. When you look at Andromeda, the light entering your eyes has been traveling for 2.5 million years. It left Andromeda when early humans were just beginning to use stone tools. That ancient light crossed the vast gulf between galaxies and arrived just now to touch your retina. You're seeing Andromeda as it was in the distant past. The galaxy has changed since that light began its journey. Stars have been born and died, but we won't see those changes for millions of years. Time and space intertwine in ways that make the universe a time machine. Look far enough and you look into the past. Galaxy clusters are groups of galaxies bound together by gravity. Our Milky Way belongs to the local group, which contains about 50 galaxies. The largest are Andromeda and the Milky Way. The rest are dwarf galaxies, small collections of stars that orbit the larger galaxies, like moons orbit planets. These dwarf galaxies are being slowly cannibalized by larger galaxies, their stars stolen away by gravity. It's a slow process, taking billions of years. Even galaxies have complex family relationships. Superclusters are even larger structures. Collections of galaxy clusters containing thousands or tens of thousands of galaxies. Our local group belongs to the Laniakea supercluster, which contains about 100,000 galaxies. Beyond superclusters, the universe shows an even larger structure, sometimes called the cosmic web. Galaxies arrange themselves along filaments with vast, empty voids between them. The universe on the largest scales looks like foam or a sponge, matter concentrated along threads and sheets with emptiness in between. The cosmic microwave background radiation is the afterglow of the Big Bang. It's light from when the universe was only 380,000 years old, cooled by expansion to microwave wavelengths. This radiation fills all of space, coming from every direction equally. It's been traveling toward us for over 13 billion years, and it tells us about the early universe's conditions. By studying tiny variations in this radiation, scientists can learn about the seeds that grew into galaxies and galaxy clusters. The past is written in light that surrounds us constantly. Asterisk, the universe is isotropic, meaning it looks essentially the same in all directions. No matter which way you look, you see similar numbers of galaxies distributed in similar ways. This suggests that the universe has no center, or rather, every point is equally the center. From any galaxy, the universe appears to expand away uniformly. This is mind-bending, but also strangely democratic. No place in the universe is special. Every location is equivalent. Earth is no more or less central than any other world, circling any other star. Time dilation is a consequence of Einstein's relativity. Time passes differently depending on gravity and velocity. Near a massive object like a black hole, time passes more slowly than far from it. For an object moving at high speed, time passes more slowly than for a stationary object. This isn't an illusion. It's real. Astronauts on the International Space Station age slightly more slowly than people on Earth. Because they're moving fast and experiencing slightly less gravity. The difference is tiny, only milliseconds over months, but it's measurable. Time is flexible, relative, not absolute. If you could travel at speeds close to light speed, time dilation would become dramatic. From your perspective, time would pass normally, but observers watching you would see your time slowed down. You could travel to a distant star and back, and while only a few years passed for you, decades or centuries might pass on Earth. This isn't science fiction. It's physics. The universe allows this, though the engineering challenges of near light speed travel remain insurmountable with current technology. Still, it's comforting to know the universe is stranger and more flexible than everyday experience suggests. The twin paradox is a thought experiment illustrating time dilation. Imagine twins. One stays on Earth. The other travels to a nearby star and returns at near light speed. When they reunite, the traveling twin is younger. Less time passed for them. This seems impossible, but is completely consistent with relativity and has been confirmed by experiments with precise clocks. Time is not fixed. It bends and flexes based on motion and gravity. The universe is more fluid than our intuition suggests. Gravity is not a force in Einstein's relativity, but a curvature of space-time. Massive objects bend space and time around them. Other objects follow the curves in space-time, which we perceive as gravitational attraction. Earth orbits the Sun, not because the Sun pulls on it, but because the Sun curves space-time and Earth follows that curve. It's like a ball rolling in a curved bowl. The curve guides the motion. This understanding transformed physics and revealed that space and time are not separate things, but aspects of a unified space-time. Gravitational waves are ripples in space-time caused by accelerating massive objects. When two black holes orbit each other and eventually merge, they send gravitational waves spreading through the universe at the speed of light. These waves stretch and compress space itself as they pass. In 2015, scientists detected gravitational waves for the first time using incredibly sensitive instruments. The waves they detected came from two black holes merging over 1 billion light-years away. The universe is not static space, but a dynamic medium that can vibrate and ripple. The detection of gravitational waves opened a new way to observe the universe. Previously, we could only observe things that emit or block light. Now we can detect events through their gravitational effects. This is like gaining a new sense. Imagine being blind your whole life and suddenly gaining sight. That's how revolutionary gravitational wave astronomy is. We're seeing the universe in a completely new way, detecting events and objects that were invisible before. Wormholes are theoretical shortcuts through space-time. If they exist, they would connect distant parts of the universe, allowing travel between them without crossing the intervening space. You'd enter one mouth of the wormhole and emerge from the other instantly, regardless of the distance between them. Wormholes arise naturally in the mathematics of general relativity, but whether they can exist in reality is unknown. They might require exotic matter with negative energy density, which may not exist. Still, the universe's laws don't forbid wormholes. They remain a possibility, however remote. The multiverse is a speculative idea that our universe might be one of many. Different versions of multiverse theory exist. Some suggest infinite parallel universes where every possible outcome occurs. Others suggest bubble universes that form from quantum fluctuations, each with different physical laws. These ideas are controversial because they're hard or impossible to test. How do you observe something outside the observable universe? Still, the mathematical frameworks that describe our universe seem to naturally produce multiverses. The question of whether we inhabit one universe or many remains open. The observable universe has a horizon, a distance beyond which light hasn't had time to reach us since the Big Bang. This horizon is about 46 billion light-years away in all directions. Beyond this horizon, the universe continues, probably forever, but we can't see it. We're trapped inside our observable bubble. Light from beyond the horizon hasn't reached us yet, and, due to the universe's expansion, might never reach us. There's a whole universe out there that we're causally disconnected from, that we can never observe or communicate with. The universe might be infinite in size. If so, then somewhere in that infinity, every possible arrangement of matter exists. There would be countless Earth-like planets, countless versions of human history playing out with slight or major variations. An infinite universe means infinite possibilities become certainties. This is strange to contemplate, but follows from basic probability. If you have infinite space and infinite time, even extremely unlikely events must occur, and occur infinitely many times. The universe might contain infinite copies of you, of Earth, of everything. The heat death of the universe is the most likely ultimate fate according to current understanding. As the universe expands and ages, stars will exhaust their fuel and die. Eventually, all stars will be gone. Black holes will evaporate through Hawking radiation. Matter will decay. After inconceivable spans of time, the universe will be cold, dark, and empty. Nothing will happen anymore because there won't be enough energy concentrated anywhere to make things happen. This is trillions upon trillions of years in the future. The universe is young now, full of light and activity, but everything trends toward equilibrium, toward peace, toward final rest. Despite this distant end, life can exist for trillions of years yet. Small, cool red dwarf stars will continue shining far longer than the universe's current age. Planets around these stars could harbor life for vast periods. Even after all stars die, other forms of existence might persist near black holes, which radiate small amounts of energy. Life is resourceful. Given energy, however sparse, life might find ways to continue far into the deep future. The universe's ending is so distant, it's almost meaningless. For practical purposes, the universe is eternal. Exoplanets are planets orbiting stars other than our sun. We've discovered thousands of them. They come in astonishing variety. Hot Jupiters orbiting close to their stars. Super-Earths larger than Earth but smaller than Neptune. Ice giants, rocky worlds, planets in the habitable zone where liquid water could exist. Some planets orbit binary star systems. Some orbit pulsars, the dead remnants of stars. The diversity of planetary systems is stunning. Our solar system is just one example among countless configurations. The habitable zone around a star is the region where temperatures allow liquid water on a planet's surface. Too close and water boils away. Too far and it freezes. Earth sits comfortably in the sun's habitable zone. Many discovered exoplanets also orbit within their star's habitable zone. These worlds are candidates for harboring life, though being in the habitable zone doesn't guarantee life. Many factors influence habitability. Still, the sheer number of potentially habitable worlds is encouraging for those who hope life exists elsewhere. The Drake equation is an attempt to estimate the number of communicative civilizations in our galaxy. It multiplies several factors, including the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life develops, and so on. Depending on the values you use, the equation can predict anywhere from 0 to millions of civilizations. The uncertainty is enormous because we don't know many of the factors. But the equation provides a framework for thinking about life in the universe. The Fermi paradox asks, why? If life is common in the universe, we haven't detected any signs of it. With billions of stars in our galaxy, many billions of years old, even if intelligent life is rare, there should be many advanced civilizations. Some might have developed technology millions of years before us. They might have colonized the galaxy by now. So where is everyone? Why is the universe so quiet? Many explanations have been proposed. Perhaps life is rare. Perhaps civilizations destroy themselves. Perhaps they exist, but we can't detect them. The silence is mysterious and somewhat unsettling, but also strangely peaceful. Perhaps the silence of the universe is simply because space is so vast and signals take so long to travel between stars. A radio transmission from a civilization 1,000 light-years away would take 1,000 years to reach us. If they sent a message today, our descendants 1,000 years from now would receive it. And if we replied, their descendants 1,000 years after that would hear our response. Conversations across interstellar distances require patience beyond human lifetimes. The universe operates on timescales that make human history seem like a brief flicker. Maybe civilizations exist, but communicate in ways we haven't thought of. We've been sending radio signals for barely a century, a tiny moment in cosmic time. A more advanced civilization might have moved beyond radio to technologies we can't imagine or detect. They might communicate using methods that seem like natural phenomena to us. Or perhaps they're intentionally quiet, listening rather than broadcasting, cautious about revealing their presence to unknown neighbors. The universe might be full of watchers, all waiting, all listening, none speaking first. Some scientists suggest life might be common, but intelligence rare. Single-celled organisms might arise easily given the right conditions. But the path from simple life to complex intelligence might involve many unlikely steps. Each step has to happen in the right sequence at the right time. On Earth, it took nearly 4 billion years for intelligent life to emerge. Perhaps we're early, one of the first to reach this level. Or perhaps intelligence is a dead end, a trait that leads to self-destruction before civilizations can spread among the stars. These are sobering thoughts, but there's also something calming about them, about accepting our uncertain place in the cosmic story. The concept of a great filter suggests that there's some stage in the development of life that's extremely difficult to pass. It might be the origin of life itself, or the development of complex cells, or intelligence, or technological civilization, or perhaps something that lies ahead of us. If the filter is behind us, we're fortunate survivors, and the universe might be ours to explore. If it's ahead, then civilizations may commonly arise, but rarely survive long enough to become interstellar. We don't know where the filter lies, or even if it exists. But the question reminds us that existence is fragile and precious. Let's think about something more comforting now. The universe may be largely empty, but it's also full of beauty. The images captured by telescopes show structures of breathtaking elegance. Nebulae glow in colors created by different elements. Oxygen produces blue and green light. Hydrogen glows red. Sulfur creates orange and yellow. These clouds are like cosmic paintings, each one unique, created by natural processes with no artist required. Just physics and chemistry producing art on scales too large to comprehend. The pillars of creation in the Eagle Nebula are perhaps the most famous example. These towering columns of gas and dust stretch several light years high. They're stellar nurseries, places where new stars are forming. The pillars are slowly being eroded by radiation from nearby hot stars, carved into these elegant shapes by light pressure and stellar winds. They're temporary structures, cosmically speaking, but They've existed for thousands of years and will persist for thousands more. When we look at them, we're seeing matter in the process of becoming stars, witnessing creation happening in slow motion. The Hubble Space Telescope has given us incredible views of the universe. The Hubble Deep Field images, taken by pointing the telescope at apparently empty patches of sky and exposing for many hours, revealed thousands of galaxies in regions where none were visible to the naked eye. Every direction we look, however empty it appears, contains galaxies beyond counting. The universe is fuller than it seems. Every dark patch of sky hides multitudes. There's something profound about that, about the hidden abundance all around us. The James Webb Space Telescope, launched recently, can see even further and in different wavelengths than Hubble. It looks in infrared light, which can penetrate dust clouds, and also shows us light that's been redshifted by cosmic expansion. Webb can see some of the first galaxies that formed after the Big Bang, when the universe was only a few 100 million years old. These ancient galaxies appear as tiny smudges of light, but each one contains billions of stars. We're looking back in time, seeing the universe as it was in its youth, watching the first structures emerge from the cosmic dark ages, black holes. Despite their fearsome reputation, are fascinating objects. They're regions where gravity is so strong that nothing can escape once it crosses the event horizon, not even light. The event horizon is the boundary of no return, the point where escape velocity exceeds the speed of light. Inside, all paths lead inward to the singularity, a point of infinite density, where our physics breaks down. We can't see what happens inside because no information escapes. The interior of a black hole is forever hidden from the rest of the universe. But black holes aren't the cosmic vacuum cleaners they're often portrayed as. Their gravitational pull is strong, but only near the event horizon. If our sun were replaced with a black hole of equal mass, Earth's orbit wouldn't change. We'd freeze without sunlight, but we wouldn't be sucked in. Black holes only affect objects that come very close to them. From a distance, they're just massive objects with strong gravity, like any other massive object. They sit quietly in space, slowly accumulating matter that strays too close, patient and eternal. The largest black holes are at the centers of galaxies. These supermassive black holes have masses millions or billions of times the sun's mass. The one at the center of our Milky Way is called Sagittarius, a star. It has a mass of about 4 million suns, but is packed into a region smaller than Mercury's orbit. Despite its mass, it's quite far from Earth, about 26,000 light-years away in the galactic center. It poses no danger to us. It just sits there, occasionally consuming gas or an unlucky star that wanders too close. the gravitational anchor around which our entire galaxy rotates. Recently, scientists captured the first image of a black hole's shadow using a network of radio telescopes spanning Earth. The image shows a bright ring of hot gas surrounding a dark center. The dark center is the black hole itself, or rather, the absence of light from behind it. Light from gas behind the black hole is bent around it by gravity, creating a circular shadow. The image confirmed predictions made by Einstein's theory of relativity. It's strange and wonderful to see these theoretical objects made visible, to have direct evidence of these extreme manifestations of gravity. Near a black hole, time behaves strangely. The closer you get to the event horizon, the slower time passes relative to distant observers. If you could hover just above the event horizon and then return, you'd find that more time had passed in the outside universe than you experienced. This time dilation becomes infinite at the event horizon itself. To an outside observer, an object falling into a black hole would appear to slow down, never quite reaching the horizon, frozen in time forever. But from the perspective of the falling object, it would cross the horizon and reach the singularity in a finite time. Different observers see different versions of reality near black holes, a consequence of the relativity of time. Wormholes are hypothetical tunnels through space-time that could connect distant points in the universe. Their solutions to Einstein's equations, mathematically possible, but probably not physically real. To exist, a wormhole would need exotic matter with negative energy to hold it open. We've never detected such matter. Most physicists think wormholes don't exist, or if they do, they're incredibly tiny and unstable, collapsing instantly. But they're a fascinating possibility, a suggestion that space-time might be more flexible than we imagine. The idea of shortcuts through the universe captures our imagination, even if reality doesn't permit them. Let's think about the future of the universe now, the very long-term future. Stars will continue forming for trillions of years, but eventually the gas will run out. No new stars will form. The existing stars will age and die one by one. Red dwarfs, the smallest stars, can burn for trillions of years. The last stars won't die until long after the current age of the universe. But eventually, they too will exhaust their fuel and fade. The universe will enter what's called the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. Even these remnants won't last forever. White dwarfs will slowly cool, becoming black dwarfs, cold spheres of carbon and oxygen floating in darkness. Neutron stars will also cool. Black holes will slowly evaporate through Hawking radiation, a quantum process that causes them to emit particles and lose mass. The larger the black hole, the slower it evaporates. Supermassive black holes will take incredibly long to evaporate, timescales of 10 to the 100th power years or more. That's a 1 followed by 100 zeros, a number so large it's meaningless to human comprehension. Eventually, in the far future, the universe will consist only of photons, neutrinos, and occasional particle-antiparticle pairs forming and annihilating in the vacuum. Matter, as we know it, will be gone. The universe will be cold, dark, and nearly empty. This final state is sometimes called the heat death of the universe. When entropy reaches its maximum and no gradients exist to drive any processes. It sounds bleak, but it's so far in the future that the time between now and then is incomprehensibly vast. And it will be peaceful, perfectly peaceful. The universe at rest after trillions upon trillions of years of activity. But even this might not be the final end. Some theories suggest the universe could experience a big rip, where dark energy's repulsive force increases over time, eventually tearing apart galaxies, then stars, then planets, then atoms themselves. Other theories predict a big crunch, where expansion reverses and the universe collapses back to a singularity. Some cosmologists propose cyclic universes that expand and contract repeatedly. We don't know which, if any of these scenarios, is correct. The ultimate fate of the universe remains one of the great mysteries. But whatever happens, it won't be for billions or trillions of years. We have time. Now think about the fact that you exist in this universe, in this particular moment of cosmic history. You live in the stelliferous era, when stars shine brightly, when galaxies are full of light, when planets orbit their suns in stable patterns. You exist after the universe has cooled enough for complexity to arise, but before it becomes cold and dark. This is perhaps the most interesting time in the universe's history, the era when matter organizes into intricate structures, when life emerges and evolves, when consciousness arises to contemplate its own existence. You're made of atoms forged in stars, arranged in patterns of incredible complexity. Your body contains about 7 octillion atoms, each one a tiny universe unto itself with a nucleus and orbiting electrons. Those atoms are mostly empty space. If you removed all the empty space from all the atoms in your body, you'd be smaller than a grain of sand. And yet, you exist. You think, you feel, you experience. Somehow, these atoms, arranged in just the right way, create consciousness, create the experience of being you. The atoms in your left hand might have come from different stars than the atoms in your right hand. Some might have formed in red giants, others in supernova, explosions, others in the outer layers of dying stars. They drifted through space for billions of years before becoming part of the cloud that formed our solar system. They were part of the disk around the young sun, then part of the planetesimals that collided to form Earth. They cycled through rock and water and air, through countless organisms over billions of years before finally becoming part of you. You're a temporary assemblage of star stuff, conscious matter contemplating its origins. And when you die, those atoms will continue. They'll return to Earth, to air and soil and water. They'll become part of other organisms, other structures. Some might eventually be launched into space to drift among the stars again. The atoms are nearly eternal. Your particular arrangement is temporary, but you're part of an ongoing story that extends far into the past and far into the future. There's continuity there, a connection to everything that's come before and everything that will come after the present moment. This moment, right now, as you listen to these words, is unique. The universe in this configuration has never existed before and will never exist again. Every moment is new, unrepeated, original. The atoms in your body are in a configuration they've never been in and never will be again. Your thoughts right now are unique in the history of the universe. This exact experience, this particular arrangement of matter and energy and consciousness happens only once. It's precious because it's fleeting, meaningful because it's temporary. But there's also continuity. The laws of physics that govern the universe have been the same since shortly after the Big Bang. Gravity has always attracted. Light has always traveled at the same speed. Atoms have always behaved according to quantum mechanics. These consistent rules create a universe that's reliable, predictable, knowable. The universe isn't chaotic or random. It's ordered, governed by laws we can discover and understand. There's deep comfort in that predictability, in knowing that the universe makes sense, that it follows rules, that it can be comprehended as you drift toward sleep. Imagine yourself floating in space, looking down at Earth, that blue marble hanging in the darkness, covered with swirling white clouds, green continents, blue oceans. Every person you've ever known lives on that sphere. Every human who's ever existed was born there, lived there, died there. All of human history, all our wars and peace, all our triumphs and failures, all our loves and losses, everything happened on that small world. It's humbling to see Earth from that perspective, to recognize how small we are, how brief our existence, but also recognize how remarkable it is that this small world exists, that conditions here allow for liquid water and stable temperatures, and an atmosphere that supports life. Recognize that you're part of something rare and precious, a living world in a mostly lifeless universe. Earth might be one of countless living worlds, or it might be unique, the only place where life exists. We don't know yet, but either way, life here is valuable. Consciousness is valuable. Your existence is valuable. You're part of the universe's way of knowing itself. Matter arranged in such a way that it can think and feel and wonder. Let that perspective calm you. Your problems are real but small in cosmic terms. Your worries are valid but temporary. The universe is vast and ancient and will continue long after you're gone. But right now, in this moment, you're part of it. You're not separate from the universe, observing it from outside. You're inside it, made of it, an expression of it. When you look at the stars, you're looking at your distant past. When you breathe, you're taking in atoms that have cycled through countless other organisms. When you think, you're using patterns of neural activity that emerge from quantum processes in your brain. You're connected to everything, part of the great web of existence. The universe doesn't need you to understand it or appreciate it to continue existing. It was here long before you and will be here long after. But while you exist, you have the extraordinary privilege of being aware, of experiencing, of contemplating these mysteries. You can look up at the night sky and feel wonder. You can learn about distant galaxies and imagine what they're like. You can ponder the nature of time and space and matter. This capacity for wonder, for curiosity, for seeking understanding, is one of the universe's most remarkable achievements. So rest now, knowing that you're safe on this small world, protected by an atmosphere and magnetic field, warmed by a stable star, circling through space on a planet that's been nurturing life for billions of years. The universe is vast and mostly empty and largely indifferent. But here, on Earth, in this moment, you exist. You're warm and comfortable. You're alive and conscious. You have this moment to simply be, to exist without effort, to let go of concerns and drift into sleep. The stars will still be there when you wake. The galaxies will continue their slow dance through space. The universe will keep expanding. Atoms will keep vibrating. Light will keep traveling through the void. All the processes we've discussed will continue, automatic and reliable, requiring nothing from you. You can rest, let go. Trust that the universe knows what it's doing because it's been doing it for 13.8 billion years and hasn't failed yet. Close your eyes now if they're not closed already. Feel the weight of your body, the solid earth beneath you. Remember that you're on a planet spinning through space, orbiting a star that's orbiting the center of a galaxy that's moving through a universe that's expanding. You're in motion, always in motion, carried along by forces too large to resist. But from your perspective, you're still at rest, peaceful. Both things are true. You're moving and you're still. You're part of the universe and you're observing it. You're temporary and you're connected to eternity. Let your breathing slow and deepen. Each breath brings in atoms from across the room, from outside, from around the world. Atoms that have been breathed by others, by plants, by animals, cycling through the biosphere. Each exhale releases atoms that will be taken up by others, continuing the cycle. You're participating in exchanges that connect you to all life on Earth. Exchanges that have been happening since life began, that will continue long after you're gone. The universe is ancient and patient. It doesn't hurry. Stars take millions of years to form. Galaxies take billions of years to evolve. The universe itself has been expanding for nearly 14 billion years and will continue for trillions more. There's no rush, no urgency, no deadline. Everything happens in its own time, at its own pace. You can adopt that pace, that patience. You don't need to hurry. You can simply be existing in this moment. This quiet, peaceful moment before sleep. And as you drift off, imagine the universe continuing around you. Stars being born in nebulae. Black holes consuming matter. Galaxies spinning in the darkness. Light traveling through space, carrying information about distant events. All of it happening simultaneously. A vast cosmic symphony of matter and energy and space and time. You're one note in that symphony, brief but essential, unique and irreplaceable. Your consciousness is the universe becoming aware of itself, if only for a moment. Sleep well, knowing that you're part of something vast and ancient and beautiful. The universe has created you, briefly, and you've had the chance to look back at it with wonder. That's enough. That's more than enough. It's everything. Rest now and let the universe continue its slow, patient, beautiful work, creating and destroying, expanding and evolving, being exactly what it is, perfectly, completely, endlessly. Good night.